Okay, cool. Let's get started. The next section we're going to cover is section 1.7, which is modeling with equations. In this section, you'll look at situations where you face word problems that involve um, interest, areas and length, mixtures, things about time and how to complete a job, and then a few others involving distance, rate, and time. There's a whole range of word problems out there, so this is just a little sampling of them, some of the more classic examples. And I think some of them are pretty easy. I'm sure you've dealt with many of these before. Like I said, this class is a lot of it is review. So I'm only going to focus on creating examples for a few of these, but a lot of them are solved in sort of the same methodology could be applied to solve a lot of these word problems. So just in general, the guidelines for helping you get through some of these word problems are here. So you want to identify your variables. You want to use as few variables as possible. Only introduce variables when you really need to, um, and clearly define them. I think you'll see the benefit of actually writing down what the variable means, because then it can get confusing down the road. Um, it would be nice if you use letters that are representative when possible, representative of whatever it is you're having it represent. So, the number of apples, you can use N for the number or A for apples, kind of thing, just to kind of help you remember what those variables represent, but also writing them down is good. You got to translate the word problem into symbolic notation. You kind of guess and check different things and make sure your equations make sense. You got to set up a model using known equations or um, something that you know to be true. Particularly, you're looking for things that are equal or something that's definitely less than. Some statement that you definitely know. And then once you set up an equation of some kind, you can use it to solve your problem. Okay, so there are different kinds, as I said, different types of word problems, but I'm just going to focus on some of the more challenging ones because we don't have that much time. So first off, let's look at a mixing problem. So a mixture problem is a word problem where you have situations of substances that are mixed. Some common examples are cement or like fruit juice concentrate or alcohol mixtures or any kind of other chemical thing, some sort of chemical titration thing where you're mixing, um, say, 100% of some chemical in water, for example, and you want to dilute it to some level. Problems like that are classic mixture problems, or like trail mix is another kind of classic mixing problem. And the key to this is to keep in mind the percentage of whatever substance you're focusing on. Um, we want to look at the percentage of the mixture, which is always going to be equal to the amount of the substance that we're focused on divided by whatever the total volume of whatever it's being mixed with. So, for example, if we're talking about sugar in water, and you're told that there are 10 grams of sugar and there's 5 liters of water, then when we divide the the 10 grams into the 5 liters, we have 10 divided by 5 or 2. The units are very important in a scenario like this, so make sure you keep track of the fact that this is grams of sugar over liters of water. But this ratio helps us establish um, the relationship we need to solve these kinds of problems. Okay, so let's just jump into an example. So for example, a manufacturer of soft drinks advertises that orange soda as naturally flavored, although it contains only 5% orange juice. Okay, a new federal regulation stipulates that to be called natural, a drink must contain at least 10% fruit juice. How much pure orange juice must this manufacturer add to 900 gallons of orange soda to confirm the new regulation. Okay, so we got a good sense of what the word problem is asking us. We got to organize this information into something useful. So let's see if we can. Oops, I just happened to. Let's go there. Okay, so we have three mixtures that we have to be concerned about. We have the original mixture, just kind of putting it here. This is my, I'm just kind of picturing it as like a glass. Wow, it's an ugly drawing. Okay, so this is the original mixture. And then to it, I'm going to add some new amount here, whatever this is. I'm going to combine those two things together. This is going to be my my pure orange juice. So this is the original. Original mix. And this is going to be pure orange juice. Pure OJ. And then when I bring them together, oh, that's really ugly. This is going to be my new mix. Okay, now let's keep track of the volume. So volume-wise, well, this is 900 gallons. That's what the original mix was. And this, we don't know how much this is. We're going to mix them together, but the question is exactly this right here. How many gallons of pure orange juice? So this is unknown. X gallons of pure orange juice. They're going to be brought together, and therefore the final mixture is going to be equal to 900 plus X gallons. A conservation of volume here. Good. Okay, as far as percentages of OJ, percent of OJ, well, this one was only 5% orange juice, right? And then, well, this is pure orange juice, so it's 100% orange juice. 5% OJ, 10%, okay. And I don't know what this is, but it should be clear that it doesn't make sense to add them together, right? Because if we just add them together, that would mean that the final mixture is 105% OJ, right? Hopefully that it makes sense that that's nonsense, right? You can't have 105% orange juice. So clearly, in this situation, you can't add the percentages, right? So that's not true. We do add these, so this one, the volume, 900 gallons plus X gallons does equal to 900 plus X gallons. There's a conservation of volume that happens, but the percentages don't work out that way, right? So 5% plus 100%, right? It's not going to make sense. It doesn't equal 105% OJ in the final mixture. Okay, but what does make sense is that we can find the volume of the pure orange juice. So the amount of pure orange juice. Amount of OJ. Okay, so how much actual orange juice is in this ginormous tub of 900 gallons of this mixture? Well, it's only 5% OJ. So if we multiply 5% as a decimal, so 0.05 times 900, let's see, 10% would be 90, and half of 10% would be 45. There's only 45 gallons of pure orange juice in the original container. Okay. And here, well, we don't know how many there are because it's 100% orange juice, but we don't know how many gallons there are. But whatever it is, it would be the same formula as this, which is going to be the percentage times the volume, which is just going to be X gallons, right? So there's X gallons of pure orange juice here. Good. And then the pure orange juice does preserve itself, right? The equation, the conservation of pure orange juice tells us that 45 gallons of orange juice in the original mixture plus X gallons of pure orange juice here, together they do give you X plus 45. Go away. They do give you what we'd expect of X plus 45 gallons of pure orange juice. Good? Questions, questions, questions? Okay, so what we've arrived at is that we have two known equations, right? The middle one is invalid, so let me just make sure to cross it out some more. This whole thing is not true, but this one is true, that 900 gallons plus X gallons should be equal to 900 plus X gallons, the total volume. And this one should also be true, that 45 gallons of pure orange juice that comes from there, plus plus X gallons from here should be equal to the X plus 45, and then over here, this should be equal to the percentage of the new percentage of orange juice that is in this mixture. So if we've done it correctly, right, the goal is to make sure that the final outcome has 10% fruit juice. So it must be true that this, from here, what we want is for this to be equal to 10% OJ. So it must be true that this is equal to 0.01, oops, sorry, 0.1, which is 10%, times 900 plus X. 900 plus X. Let me get a new thing. All right, so let me write down the equations again. So we have that 900 plus X gallons was equal to 900 plus X. So this was the original volume was 900 gallons, and then I'm adding X gallons of pure orange juice. So together the total volume is 900 plus X, right? So this is the total volume. Total volume of new mix. Okay, the original mixture had 45 gallons of real orange juice plus X gallons of 100% orange juice. Together, they'll give you 45 plus X gallons, sure. And then, hopefully, if we did this right, the goal was to make sure that our final mixture was 10% orange juice. So if we multiply these two, this is the statement that we want to solve. Good. Okay, so if we distribute this 10% here and over there, we get to 45 plus X equals to 90 plus 0.1x. There's only one variable, an x, and the power of that variable is 1. There isn't any operations that's going to change that. We're not squaring anything. We're not square rooting anything. So this is going to be a linear equation. In order to solve it, all I have to do is move the terms that have an x to one side and all the terms that do not have an x to the other side. So let me subtract 0.1x from this side and from that side to give me 45 plus 0.9x equals to 90. And now I can subtract 45 from this side, minus 45, minus 45, and that gives me 0.9x equals to 45. And so x equals to 45 divided by 0.9, should be 50. Yeah, 50. X equals to 50. Okay, so let's check it. Let's put it over here. Let's see if it makes sense. So we started out with 900 gallons of the original mixture, and according to this formula, it's saying that if we add 50 gallons of pure OJ, so this is the original mix, plus 50 gallons of pure OJ, we'll end up, of course, with 950 gallons of the new mixture. Okay. If the new mixture really is 10%, then 10% OJ, then here we could say that 0.1 times 950, that's 95 gallons of pure OJ in this new mixture. Pure OJ. Okay, and then over here, well, the original mix was only 5% OJ, so 0.05 times 90. That was going to be 45. So the original mixture had just 5 gallons of pure OJ. And now, thanks to this new regulation, they had to add 50 gallons of pure OJ. And now that makes sense. 40 plus 45 gives you the 90 gallons in the mixture. So it makes sense that this is the answer. Add 50 gallons of pure OJ. Any questions about this? No? So the key to all these is to really organize your word problem. I like to come up with these kind of container things like this to symbolize them. So one container to represent the original, and then maybe something that you're adding. Also, sometimes you're subtracting things. So for example, this exact same question could have been phrased a little bit different. They could have said that they're going to remove some amount of gallons from this one. Maybe the container can only hold 900 gallons, right? The answer to this was add 50 gallons and you get it's already filled to the very brim. So what you first have to do is subtract some of the original mixture and then replace it with pure orange juice, and your goal is so that the new mixture has the 10% orange juice, right? So it's a slightly different question. So let's just set that up. Right, so if we have the original here, original mixture, which was only 5% OJ. And then from it, we're going to subtract some amount. Right? So we don't know how much we're going to subtract. We're going to subtract X amount of this mixture. And so this one is 900 gallons. 900 gallons. And we're going to take away from it, I don't know, X gallons. We're subtracting, and well, we're subtracting the original mix, so the thing we're subtracting is 5% OJ. 5% OJ. 5% OJ. We are going to replace it with the exact same quantity, so it's the same volume. We're going to replace it with the same volume of pure OJ. X gallons of pure OJ, except so then this would be 100% OJ, right? And again, we want the same conclusion, that I want my final mixture to be 10% OJ. Except I want this to be exactly 900 gallons. Good? Okay, well, conservation of volume tells us that if I start with 900 gallons of the mix, and then I subtract X gallons of that mix, throw it away, drink it, whatever, get rid of X gallons from the original mixture, making room for me to add exactly X gallons of pure orange juice, mix the whole thing together, I still get 900 gallons, right? Conservation of volume. 900 minus X plus X gives you 900. Okay, but now if we focus on the actual amount of pure orange juice, from here we get that we would have 0.05 times 900. That's how much pure orange juice is in the original mixture. We already know that that's 45. Okay, and then from it, we're going to subtract X gallons of the 5%. So that would be 0.05 times X. And to it, we're going to add X gallons of 100% orange juice. So that's going to be X. And then again, we want the final mixture to be 10% orange juice. So I want this whole thing to be equal to 1.01 times 900, which is 90. Good. Combining these two like terms, we can simplify this to be 45, 0.05, negative 0.05 plus 1 is going to give you 0.95, positive 0.95x. Right, so if this is 5%, this is kind of like an invisible 1 here, so this is like 100%. So 5%, 100%, subtract them to get positive 95%, equals to 90. Good. So subtract 45 from both sides.
Wait, how did you get 0.95 again?
Oh, sure. So I'm getting it from the combination of these two things. They're like terms. So there's different ways to look at it. You can think of it.
Oh, yep, okay. Yeah, there's a little one.
Yeah, okay. Just in case someone else has the same question, let me just do it here. What we can do is factor out an x, right? So we have negative 0.05 plus 1, and then we factor out an x. X times this is this guy. X times 1 is that guy. And then when we combine them, keeping in mind that this is a minus here, that's how we get the 0.95 or 0.95 x. You know, sometimes it's just easier to think of the concept rather than focusing on the actual arithmetic, because this is 5%. Right up here we have it. We have 100% OJ, positive 100% OJ, minus 5% OJ. Together they got to give you 95%. Okay, so now we solve for x. We get a minus 45. So we end up with 0.95. 0.95x equals to also 45. So x equals to 45 divided by 0.95, which gives you 45 divided by 0.95, 47. So I'm getting that this is approximately equal to 47 point, and let's just round to 4 decimal places, 3684. 3684. Good. And so now let's just check it. Is it true that if we remove 47.3684 gallons from the 900 gallons and replace it with 47.3684 gallons of pure orange juice, does that give us a new mixture that's going to be 900 gallons, and it is in fact 10% orange juice? So let's just set that up and check it. Well, volume-wise, it makes sense, right? Because we have 900 gallons to begin with from the original mix, and then we're going to subtract 47.3684 gallons of the original. And then we subtract 47.36 gallons of the original. And then we're going to add exactly 47.3684 gallons of pure OJ. So in terms of the volume, it makes sense. The final thing is still 900 gallons. Okay, so we have to focus on the actual orange juice. So we knew that the original mixture was only 5% orange juice. So 0.05 times 900. And then from it, so this is going to be 45 gallons of pure orange juice in the original mixture. From it, we started out this process by removing these gallons from there, which are still 5%, right? The original mixture is still 5%. So we removed 5% of the 47.3684 from there. So let's multiply those. So times 0.05, 47.3684 times 0.05 gets me 2.3684, right? So this is the amount of pure orange juice that was removed when I removed 47.3684 gallons of mixture from the original mix, right? So when I took out these 47 gallons, a little over 2 gallons was pure orange juice in that original mix. Good. And to it, I'm going to add 100% orange juice. That's 47.36. So these are going to be the gallons I add to it. So I'm going to add 47.3684. And I don't have to do a multiplication since it's 100% orange juice. Or if you'd like, you can set it up as 1 times that since it's 100% orange juice. Okay. And if I did my job correctly, we know that the final mixture was supposed to be 10% OJ. So it should be 0.10 times 900, or 90 gallons. And I can already see that that's going to work out. This one and this one combined to give me exactly 45 gallons. The original was 45. And together, they add up to give me the 90 gallons. So it does make sense. This is how much you need to remove from the original 900 gallons. Remove 47.3684 gallons from the original mixture and replace it with 47.3684 gallons of pure orange juice, and you will end up with 900 gallons of a new mixture that's 10% orange juice. Good. Questions? So I think these two should be good, good examples to help you set them up. All right. This one is a little simpler where you don't have to remove anything. You just have to add something to it. Just keep in mind that there's a conservation of volume that happens with the total and a conservation of volume with the specific object that we're keeping track of, in this case, orange juice. Any questions before I move on to a different type of question, a different type of word problem? Well, actually, let's see what the author did. So there's different ways to organize the information. So going back to the original version of this, here's some nice graphics for this. We had 5% orange juice in the original mixture. It was 900 gallons. Then we were adding 100% orange juice, X gallons of that amount. Together they combined to give you 900 plus X gallons. And we wanted it to be 10% orange juice. So they set up the same equations that we did earlier. 5% times 900 is 45 gallons. There are X gallons of pure orange juice, so 10% times 900 plus X gives you the amount of pure orange juice in the final mixture, and so that gives you the equations that we need in order to set up a solution, and yeah, they got to the same answer we did. Okay, problems involving jobs that need to get done. So these are classic problems where they say, one person is painting, Becky is painting, and then Tom is painting separate, and what if they paint together, right? Those kinds of classic situations. So the key to these is to figure out what proportion of the job can get done in 1 unit of time, and then set up an equation from there. Okay, and now the unit of time could be anything. It doesn't matter whether it's in 1 hour, 1 minute, 1 day. Just make sure that they're consistent. That's another place where they try and trip people up, because they might say that Tom can paint a house in 2 days, but Becky can paint a house in 3 weeks. So they're just kind of mixing days and weeks. So just make sure they're all in the same units of time. And then the key is going to be to divide 1 divided by h, where h is the total time it takes for one person to complete the task. And then 1 over h will be what proportion of the task gets completed in 1 unit of time. Good. For example, let's see, because of an anticipated heavy rainstorm, the water level in a reservoir must be lowered by 1 foot. Well, okay, it's a poor choice of numbers, I think. Opening spillway A lowers the level by this amount in 4 hours. So spillway A, right? You just open a faucet somewhere and let some water out of this reservoir, and it can lower the water level by 1 foot in 4 hours. Whereas opening a smaller spillway B does the job in 6 hours. Okay, so a separate place where you can release water will lower the reservoir level by 1 foot in 6 hours. So how long will it take to lower the water level by 1 foot if both spillways are open? Okay, so the key here is to combine both of them and just sort of divide them. So for spillway A, it takes 4 hours to do the entire job. 4 hours to do the job. So therefore, in 1 hour of time, just doing this, spillway A will complete in 1 hour. Spillway A completes 1 over 4, or 0.25, or 25% of the job. Does that make sense? It takes 4 hours to do the entire thing. So assuming that everything is consistent throughout, then if you come back 1 hour later after you've opened it, then they will have completed 25% of the job. Good? Questions? Okay, now spillway B. Well, spillway B takes 6 hours to do one job. Be careful that they're both the same job. In this case, lowering the reservoir level by 1 foot. So that's another place where the word problem can try and trick you a little bit, because maybe the information about how fast spillway B works might be presented in a different way. Like they might say spillway B can lower the reservoir level by 2 feet in 6 hours. So then you have to make sure that you half that, because we want the job in this case is considered to be lowering it by 1 foot, not by 2 feet. So they could try and confuse a little extra, add a little extra turn to this problem by adding that extra little piece of information. But luckily in this case, everything is consistent. They are talking about the same job. The job is to lower it by 1 foot. Okay. Anyway, so if spillway B completes the job in 6 hours, then in 1 hour, coming back to the same unit of time, in 1 hour, spillway B completes 1/6, right? 1/6, which if we turn, well, I don't know, I should put it over here. Completes 1/6, and if we turn that into a decimal, 1 divided by 6 is going to be equal to 1667. Is equal to 0.1667, or approximately 16.67% of the job. Good. You can kind of imagine, well, maybe it's easier with a different kind of mixed-in problem. Never mind, I don't want to do it that way. Okay, so now we have them both separately. This one by itself can do 25% of the job in 1 hour. This one by itself can do 16.67% of the job in 1 hour. So if they were both working together, A and B together, well, they should be able to do A plus B work in 1 hour. So in 1 hour, space. So A plus B together, A plus B spillway together. Well, together they can do the job in A plus B time. So what we want to do is recognize that together they can do 1/A plus B percent of the job. I shouldn't say that. They can do together, so they can do it in some unknown amount of time, right? That's the whole goal here. So let's go together, X hours to do the job. This A by itself takes 4 hours. B by itself takes 6 hours. Together, I don't know, how long will it take them to do the job together? Now, obviously, it won't take them 6 hours plus 4 hours. It will not take them 10 hours. It takes 4 hours for A to do it by itself. It takes 6 hours for B to do it by itself. So it doesn't make sense to add them together. 4 plus 6 makes 10. So it would take them 10 hours together. That doesn't make sense. It should be something smaller than 4, right? Because by itself it could do it in 4. So if it's getting some help, it should definitely do it in less than 4. Okay, but we don't know what that amount of time is. But I do know that if we follow the same pattern, If it takes X hours to do the job together, then in 1 hour, combined, they complete 1 over X percent of the job. 1 over X percent of the job. Good. And so now it's these things that we want to set up, right? Because they're all in 1 unit at a time. In 1 hour, we complete this percentage of the job. In 1 hour, we complete this percentage of the job. And so in 1 hour, we also complete this percentage of the job combined. So we want to set up the equation that it must be true that 1/4 plus 1/6 must be equal to 1 over X. Good. Questions? Okay, so let's get rid of this. Okay, so we have 1/4 plus 1/6 must be equal to 1 over X. Now we just have to solve for X. The LC, least common multiple for all of these terms is going to be 12X. Let's see, least common multiple equals to 12X. Obviously, X goes into that, 6 goes into that, and 4 goes into that. So what we want to do is multiply both sides of this equation by 12X. 1 over 4 plus 1 over 6. 1 over 6 equals to 1 over X. We want to multiply this side by 12X. Multiply this side by 12X. And then when we distribute, we simplify life a little bit. And we'll end up with 3X plus 2X equals to 12, which gives us 5X equals to 12. And so we end up with X equals to 12 divided by 5. So X equals to 2 2/5 or 2.4. Good. So remembering what X represents, going back to up here, X represents the hours that it takes for them to do the job together. How long will it take to lower the water level if both? Okay, so it'll take 2.4 hours. 2.4 hours and 2.4 hours. And most people don't really like to have hours represented as a decimal, right? If you tell someone to do something for 2.4 hours, the most common thing that people will do is 2 hours and 40 minutes, right? And that's not true. 2.4 hours is not 2 hours and 40 minutes. This is going to be 0.4 of an hour. Kind of like if it was 2.5, 2.5 would be 2.5 hours, and 0.5, half an hour, would be 30 minutes. Right, so what we need to do to really translate this is to multiply 0.4, the 0.4 from here, times 60 minutes. Now, this is going to be equal to 24. Right, because 10% of 60 is 6, and 6 times 4 is 24, so 24 minutes. So that's our answer. We want to open both spillways. Open both spillways. A and B for 2 hours and 24 minutes. and the reservoir level will be lowered by 1 foot. Any questions? No? 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 Okay. Let's see how they organized it. This thing. Yep, same thing, 1/4 plus 1/6, right? The fraction of the work done by A, the fraction of the work done by B equals to the fraction of the work done by both of them combined together. So that's really the hardest part of these word problems, setting up the equation that you need. And so 2 hours and 24 minutes. Good. Problems involving distance, rate, and time. So the formula we want to keep in mind is that the distance equals to the rate times time. Whether this red is either a constant speed or an average speed of a moving object, okay? For example, driving 60 miles per hour for 4 hours takes you a distance of 60 times 4, 240 miles. Okay, I feel like the other version of this, which is completely related, rate, which is the same sort of thing as speed, right? So rate and speed in these word problems are going to be very synonymous here. And I feel like speed, if you think of speed, how fast you're going, 60 miles per hour, for example, speed is defined to be the distance over time. Distance traveled over time elapsed. You went 60 miles per hour, you went 400 meters per second, whatever. So some sort of distance traveled in a unit of time gives you the speed. I feel like this is easier to memorize or remember. And then from here you can get all three versions of this. If we multiply both sides of this equation by time, then the times cancel on the right-hand side, and then you're left with speed times time. Right, if we multiply both sides of them by time, we end up with time times speed equals distance, which is this. Distance equals to the rate times the time. The rate is the speed. And then we've solved for speed. We've solved for distance. We can also solve for time. If we divide both sides of this equality here, or this equality, by the rate, we get to solve for time. So divide everything by the rate, or the speed, and we get to the other version of this, which is that time is equal to the distance traveled divided by the rate or the speed. So here are the three versions of this that will help us with all these word problems. So if they give you distance and they give you time and they're asking you about speed, then this is the one you use. If they give you the time, they give you the speed, and they're asking you about the distance, well then this is the version we need. And this is the most common one that we use in these word problems, that they give you the distance, they give you the speed, and then they're asking you about time. So this is a pretty useful one there. Questions? So here's an example. Let's see. A jet flew from New York to Los Angeles, a distance of 4,500 kilometers. The speed on the return trip was 100 kilometers per hour faster than the outbound speed. If the total trip took 13 hours of flight time, what was the jet's speed from New York to Los Angeles? Okay, so let's pull out my awesome drawing skills. We got LA over here. Let's see if we can draw a map of the US. Something, I don't know, and there's Texas, and then there's Florida. I don't know, something like this, and there's something over there, and I don't know, something like that. There we go. Okay, so here's LA, here's New York, and then, you know, things there. All right, so we go from there to there, and then we also want to go back from there to there. And of course, the distance is the same in both cases. So the distance in either direction, distance, let's just write down the things we know, equals to 4,200 kilometers. Be careful that the units are consistent, that they match, and they do here, 100 kilometers faster than, right? Because they could have made it a little harder and said that the speed on the return trip is 500 miles per hour faster than, well, that seems like way too much, 50 miles per hour faster than the other direction, something like that. And then you'd have to be careful to match the units. But luckily here, we got the same kilometers, and we're using hours, and it took 13 hours, so all those units match. Okay, now the speeds. The speed for the return trip, so flew from New York to LA is the first direction. So from in this direction over here is sort of the first leg of the trip, and then you came over here and that was the second leg of the trip. So first we go this way and then we go this way. And on the first leg of the trip from New York to LA, okay, the speed on the return trip was faster. And the total time it took is 13 hours. So total time is 13 hours. Time. Oh, how do I organize this? Let's put on the first from New York to LA. We had speed is unknown, right? I don't know, some x speed. The distance, well, the distance was 4,200 kilometers, and the time, well, I don't know what the time is, but we have our formula for the time. Time equals the distance divided by speed, this third version of it. So whatever it is, it would have been 4,200 divided by x. On the other way around, we have from LA back to New York, the speed, well, again, I don't know what the speed is, but we are told that the speed was related, and it was 100 x plus 100. Right? Like if this was 400 miles an hour, kilometers per hour, this one would be 500 kilometers per hour. So this one's going to be 100 kilometers per hour faster on the outbound. Wait, the outbound. The speed of the return trip was, yeah, the return trip was 100 faster than the outbound. Okay, and so the distance covered is still the same. Distance covered is still 4,200 kilometers. And the time, well, again, we use the same formula, that the time is equal to the distance traveled, which is 4,200 kilometers, divided by x plus 100. Good. And now the final piece of the puzzle is that the entire round trip should have taken 13 hours, the total trip. So it must be true that the time it takes to go from leg one of the trip, from New York to LA, this amount of time, plus this amount of time, the amount of time it took to go from LA to New York, that these two together should add up to 13. And there's your equation. 4,200 divided by x plus 4,200 divided by x plus 100 should be equal to 13. Good. So now we just have to solve for x from there. That's going to be ugly, but at least we have the equation. So let's set it up. So again, we had 4,200 divided by x plus 4,200 divided by x plus 100 should be equal to 13. Okay. So let's get rid of the fractions as the first step here. So I'm going to multiply both sides of the equal sign by both of these denominators. So let me copy it again. Well, I'll just do it. So this is equal to multiplying this by x times x plus 100 on the left-hand side of the equal sign. And on the right-hand side, I do the same thing, x times x plus 100. When I distribute, the x's cancel here, and I'll end up with 4200 times x plus 100. Plus, and then 4200 times just x by itself equals to this, 13x, x plus 100. And that's going to get ugly. So this is going to be 4200x plus 4200, and then multiplying by 100 means I just add a couple extra zeros, and that's going to get me to 420,000 plus another 4200x equals to 13x squared plus 100, right? 13 times 100, just add 2 zeros to the 13, x. So that looks pretty ugly. I think this is going to be something where we use the quadratic formula. So I don't think it's going to work out very nicely. Okay, so 4,200 plus another 4,200, that makes it 8,400. So combining these two gets to 4,800x plus 420,000 equals to 13x squared plus 1300x. So I'm going to move everything to one side, shift it over to one side so that we can use the quadratic formula. So I'm going to subtract minus 8,400x minus 8,400x. So 1,300 minus 8,400 gets me to 7,100. And I'm going to move minus 420 here, minus 420 here. So I'll end up with 0 equals to 13x squared minus 7,100x minus 420, 1, 2, 3. I don't know why I didn't add the extra zeros. Okay, that looks pretty ugly, so this would be a fantastic opportunity to take advantage of the quadratic formula. Remember, the quadratic formula was derived to solve exactly this. Right, something that fits this form, and that's this. So all we have to do is identify the roles here. The role of A is being played by a 13. The role of B is being played by a negative 7,100. And the role of C is being played by negative 420,000. So we can solve for x using that formula, right? So the formula is x must be equal to negative b plus or minus square root of b squared minus 4ac all over 2a. And so x is equal to negative b. Now, if b is already negative 7,100, so this must be positive 7,100 plus or minus, and it's going to be negative 7,100 squared, so that'll get rid of the negative. B squared minus 4 times a times c, which is also negative, negative 420,123. All of that is in a giant square root, and all of that is divided by twice a, 2 times 13. Okay, well, all we have to do is get our calculator, start crunching some numbers, and hopefully, let's see what the author did. Okay, so s speed from, okay, that's what we did. Yep. And then you set up the same equation, okay? And then, yep. Okay, that's exactly what we got. And then we can punch it into our quadratic formula. Oh, good. It's not too bad. So you end up with two solutions. You get S equals to 600 from the quadratic formula, right? This is the exact same formula that we were using. So this is what we got. And when you punch it into your calculator, you end up with this. So we either get this value right here, S equals to 600, or S equals to negative, right? So S represents the speed from in one direction, from New York to LA. So speed can't be a negative 53. It just doesn't make sense. So we can just kind of automatically ignore that one. And then this one we want to check just to make sure it's true. So S represents the speed. We reject the negative answer. We conclude that it must have been 600 kilometers per hour from New York to LA. And therefore it must have been 700 kilometers per hour in the other direction. Good. Any questions?
Yeah, for that negative 53.8, does that translate into anything like you shaved off 53.8 minutes, or is that just completely
it doesn't make sense in our real world solution sets, right? So it's an equation. It's a value that solves the equation. So if I went back to the quadratic formula that we were working with, say this one, this equation right here, this is saying that I can plug in that negative into these values and still get a true statement. So it solves this equation, but it doesn't relate back to our real world problem. It doesn't make sense because S is the speed of the plane, so it's saying that it's flying in reverse. If you fly in reverse at 53 miles per hour, that you're somehow going to get there, and it just doesn't make any sense at all.
Okay. Thank you.
Now, it doesn't make any sense in the context of this word problem because it just doesn't make sense that the plane would be going in reverse by 53. But there are certainly word problems out there where this might be a good solution. In fact, maybe we're looking for a negative solution, right? If we're looking at a case where we're talking about how many feet below the water, something about a submarine or something, then we go, oh yeah, we're looking for negative because that's below the water line. And so maybe the negative is the only one that makes sense in a situation like that. Or if we're looking for credit card debts, how much below zero you need to go before something happens, or like, okay, I'm looking for a negative. So in some cases you're looking for negatives, they make sense, but in some cases they don't. Some cases both make sense. So you just really have to take a minute and think about your word problem and what the values of these variables represent, and then make sure that they give you solutions that are consistent.
Okay. Thank you.
Sure, no problem. Sometimes, even worse, sometimes both of them are silly, right? Sometimes we get two terrible answers that don't make sense. You're like, oh, okay, that this problem doesn't have a real solution. It has this phantom mathematical equation solution that doesn't really relate to the real world, right? Math is not the real world. Math is a way of representing, in a simplistic way, many of the real things in the world. And we add more and more sophistication and complication to our equations so that we can make our math equation be a little bit more like the real world, but it's never actually the real world. So, sometimes we get weird things. And, sometimes we can't solve it. We very often get to a point where we end up with an equation that does a pretty good job of solving the situation, but then we get stuck and we're like, okay, well, we have the equation, but now we don't know how to solve it. So then we do lots of things to get a pretty good approximation to it. It might be a computer model that just kind of guesses and checks different things until we get kind of close. Or a variety of techniques that either simplify it, like we don't know the exact answer to this one, but we can find a way to get a similar kind of equation that's close. Just different things that we try to approximate it. That's particularly true if any of you are interested in like rocket science, aeronautical engineers. there's a lot of equations we run into where we know that's the equation, like this is the equation we want to solve, but then we just don't have a way of solving it. It's too complicated, too many variables, too many powers, we don't know how to solve it. So then we begin to come up with ideas, either mathematical equations or ways of simplifying it or ways of approximating it. And then very popular as computers get ever more powerful, an increasingly popular way of finding the results or approximating the results is to just have a computer model recreate, the settings that they need to be able to produce an approximation that works. Okay, any questions? No? No? During the Cold War with Russia, when we were kind of racing to see who gets into outer space and rockets and all that, there's quite a bit of like the math associated with solving some of these problems for the rockets. There was sort of a math race going on as well, to see who can come up with approximate solutions to the same kinds of issues that both aerospace programs were facing. Oh, I know it's another interesting application or sort of idea of getting stuck with equations. Have you guys ever seen, there's the B-2 bomber, the stealth B-2 bomber, and then there's the other one. It's called something fighter? Let's see. B-2 stealth bomber. There's this one. Right, so there's this very famous airplane that you can see here. You can make it a little bit bigger. There's this one. And then the other one is it F2 fighter? Which one's the F2 fighter? F2 fighter. No, that's not it. Stealth fighter. Who's the stealth fighter? This one's what you want to look at. Okay. Do you see have you noticed how this fighter is made up of a bunch of straight, flat panels? Flat panels all over the place? Compared to this one, this stealth technology gave us nice, smooth, round curvatures, right? All around the cockpit, nice and smooth and round, versus this fighter, which is made up of a bunch of straight panels. Right? If you're wondering why that is, so we came up with equations. The equations involved with making this fighter be stealth. It involves reducing its radar signature. And the equations that we created were very, very complicated. So this airplane was originally kind of envisioned and designed like in the late 70s, I think. And at the time, the computers that were available at the time were not sufficiently powerful to solve those equations for curvatures. So they had to limit themselves to flat panels because the computers could not didn't have the computing power to model a curvature. By the time so they developed this one first, they designed it. By the time they got around to designing this one, this was probably like the early 80s to mid 80s, and by then the computers had improved, and then, the computers had improved, and now it was possible for them to come up with approximations to those equations when they gave you nice curvatures, and so we improved our ability to produce something just based on the computing power available. So that sort of reminded me of this whole thing here, where in this case it was a really nice equation and we could just use the quadratic formula, but it's not hard to imagine how this equation could get really ugly, different variables, different powers, and get to a point where it's not really solvable. Remember, the quadratic formula only applies to this very simple case of having a situation where we have, where do we go? I thought I had somewhere. Where are it? Of this very simple case where we have 0 equals to some constant x squared plus some variable x plus a constant. So if we have this exact scenario, then we can use the quadratic formula. If this was a cubed here, then it wouldn't apply. Or if we had two variables, if we had x, y, then it wouldn't apply. Right? So it's only applicable to a very limited number of situations. Okay, any other questions? No? No? Okay, cool. Let's take a little 10-minute break and then we'll come back with the next section, 7.8. Okay, moving on to inequalities. This should be the easiest section we've covered so far. We won't spend much time on it. 1.8, inequalities. So here we'll be looking at solving linear inequalities, solving non-linear inequalities, absolute value inequalities, and then a little modeling with inequalities. So, inequalities, right? So often have to describe the solution in terms of a graph, a picture that describes all the solutions, and it's typically a segment of the number line that will solve these, that will represent the solution set. So to solve inequalities, we get to work with the inequality in the same way that we would solve an equation. We just have to observe some additional sort of properties of inequalities, that's all. So if the equation had been 4x plus 7 equals to 19, then what we would do is subtract 7 to both sides, divide by 4, and we would arrive at an answer x equals to 3. With an equation, there's only one value that makes it exactly true. Replacing the x with a 3 makes it true. When we have the inequality, well, we do the same thing, subtract 7, divide by 4, and we arrive at the statement that x must be less than or equal to 3. And so here, this graph right here describes all possible answers, right? Anything in this segment of the number line can be replaced. The x can be replaced by any value in this segment of the number line, and we always get a true statement. Okay, so the only thing we really have to do is sort of examine what are the properties of inequalities that are a little bit different than addition. So let's look at these. So here are the properties we have to be careful of. So if we have this inequality, a is less than or equal to b, this means that is equivalent to. So if we have this, it's equivalent to this. That's what this double arrow thing is saying. So this first rule is saying that we can always add a value to both sides of the inequality and maintain the same direction of the inequality. Good. This second one is saying that we can always subtract the same value from both sides of the inequality and still maintain the inequality. Note that in both of these cases, the c is either positive or negative. It doesn't matter either way. So the inequality stays the same whenever you add or subtract any constant. That's really all we really want to get away from this. Okay? Adding or subtracting any number to both sides of the inequality maintains the inequality. Okay, on the other hand, now if we just focus with positive numbers, then if we have an inequality and we multiply both sides of the inequality by that positive number, then we maintain the inequality. Right? So the first three rules here really are exactly the same as an equation. Right? You can add or subtract to both sides of the equation. You can multiply both sides of the equation by a positive number. Let's skip this one for a second and jump to this one. Also, if wait, no, that's not what I want to do. Never mind. Okay, so let's back to number 4 then. So now, on the other hand, though, if c is negative, right, less than 0 means that the constant is negative. Well, this rule is saying that if we multiply both sides of an inequality by a negative number, then the new result is going to be almost the same as before, as what we would expect, but the direction of the inequality changes. That's all. So let's do an example of that part there. So what this is saying is if we start off with something that's true, like 6 is definitely less than or equal to 8. That's definitely true. And we decide to multiply both sides by a negative number. So if we multiply the left-hand side by, say, -2, -2 times 6, and then multiply the right-hand side by -2, -2 times 8, then we're going to end up with -16. And over here, we're going to end up with -12. And the relationship between -12 and -16 is that -12 is greater than or equal to. So we had to change the direction of the inequality. If you ever get confused about which one's bigger and which is smaller, remember that we can always think about it on the number line. So on the number line, numbers get larger in this direction. Always. So we have 8, we have 9, we have 10. Numbers get larger this way. So they get smaller in this direction. So going in this direction, we get smaller. And that is also true on the other side of the 0. So we have 0, we have -1, we have -2, we have -3. So numbers get smaller in this direction, and they're larger in that direction. So if we think about it from that perspective, then as we kind of extend this out here, then -16 is going to be over here, and -12 is going to be over there. So that's why it's true that -12 is larger than -16. Another way of thinking about it is kind of debt. If this is 0 and you're into debt, then someone that is only $12 in debt is wealthier than someone that is $16 in debt, right? You're closer to being out of debt, right? The inequality symbol will always face this direction on the number line. Some people think of this as the little Pac-Man guy. The little mouth of the Pac-Man guy always faces the larger number, and on the number line, it always faces that way. Okay, the next property says that if A and B are both positive, and we have an inequality that is true, this one, then what happens when we flip it over and do 1 over A and 1 over B? And so the direction of the inequality changes. Again, let's take a look at an example that illustrates that. So for example, I definitely know that 2 is less than or equal to 4. That's absolutely true. That's kind of like this right here. But what happens when I flip them over 1? So 1/2 compared to 1/4. So now what's bigger? The 1/2 is bigger than the 1/4, right? 1/2 is 0.5 and the 1/4 is 0.25. If that makes more sense. Either way, I know that the direction of the inequality has changed. Good. So that's what happens here. It's a useful property. And if A is less than B and C is less than D, then A plus C is less than B plus D, right? So in this inequality, this one is the smaller, this one is the larger. In this inequality, this one is the smaller, this one is the larger. So this property is just saying that if we add up together the two smallest ones, right, the smaller one plus the other smaller one is less than or equal to the larger one plus the larger one. That makes sense? Good. Okay, if A is less than B and B is less than C, then A is less than C. Good. So this one is less than the B, and then it's very important in this case that this is the same value there. This A is less than B, but B is less than C, so then we can connect it and say that A must be less than or equal to C. That's what that last property is. Okay, so as long as we keep track of these properties, then these problems should be easy to work with. We do all the same operations, the same methodology that we would with an equation. We just have to keep track of these new principles involving inequalities. If we multiply, and therefore by extension divide, by a negative number, we got to change the direction of the inequality. And if we flip both sides of inequality over 1, then we change the direction of the inequality. And then we can use properties 6 and 7 to kind of condense two different inequalities into one. And in some word problems, that's actually pretty useful. Okay, so let's look at some examples. Parent, pay attention to rules 3. Okay, so it's fine. And inequality is linear if each term's constant multiple variable to solve inequalities. Okay, so here's an example. Solve this inequality. 3x is strictly less than 9x plus 4. So we would approach this in the same manner that we would if we had the equation. 3x is equal to 9x plus 4. There's really very little difference. Right? We just have to keep track of that inequality there. So to solve this one, let's see, since it's linear, I know that all I have to do is put all the terms that have, well, you know what? Let's do it that way. Let's move this one this way, minus 9x minus 9x. That'll give me negative 6x equals to 4. And then x equals to 4 divided by negative 6. So x equals negative 2/3. Okay, well that's what it would be like if it was an equal sign. So now let's compare that to an inequality. 9x plus 4. We follow the same steps. Let's subtract 9x from both sides, minus 9x minus 9x. We know that adding or subtracting values to both sides of an inequality does not change the direction of the inequality. So this stays the same. 6x is less than, strictly less than, 4. And now we have to divide both sides by negative 6, which is equivalent to multiplying both sides by negative 1/6. So the rule didn't specifically say anything about division, but when we divide both sides by 6, that's the same thing as saying let's multiply both sides by negative 1/6. Right? This is same as saying negative 6x is less than 4 and saying I'm going to divide this side by negative 6, divide this side by negative 6. Right? Same thing. Oops. Cancel that. We end up with something involving the x. Now, the point we want to drive at, though, is that we know that we have a rule that if we multiply both sides of the inequality by a negative number, we got to change the direction of the inequality. Okay. So that gives us x is greater than negative 4/6. And then same thing over here before I forget to change it. That way. Okay, so now x must be strictly greater than negative 2/3. On the number line, think about where that is. So here is 0. Let's say that this is negative 1. So negative 2/3 is going to be not quite at negative 1. So there's negative 2/3 right there. And here's positive 1 over here. So it's got to be greater than that. So I can describe it with an open circle or a parentheses and greater, so on bigger values, so that way. So all of these values over here can replace the x to make it a true statement. We can take a couple of those just to guess and check, just to make sure. And an easy one to do would be the value 0. It's in there. So if this is true, I can replace the x with a 0. Replace the x with a 0. And that should give me a true statement, and it does. 0 is less than 4. Right? I can also replace it with a 1. That's a nice, easy one to check. So if I replace it with a 1, it would say that 3 is less than 9 plus 4, which is 13. So yeah, that's also true. Good. We can check to make sure that this side doesn't work. Negative 1. Okay, if I replace it with a negative 1, negative 1, negative 1, that gives me negative 3 is smaller than, less than, negative 9 plus 4. Negative 9 plus 4 is negative 5, and we know that that's not true. On the number line, the negative 5 is on the left-hand side of negative 3. So someone who only owes negative $3 is wealthier than someone that owes negative $5. Right? So this is no longer true. That's why negative 1 is not part of the solution set. Good? Not true. X equals negative 1. Okay, any questions? No? No? Okay, so Lothar did the exact same thing. We can also use an open circle instead of parentheses, and we can also describe the exact same set using interval notation by describing it this way. Negative 2/3 out to positive infinity. Okay, solving nonlinear inequalities. All right, well, if we end up with something a little more complicated, a nonlinear inequality, then very often what we end up with is something that can be solved by using this idea that if we have a multiplication of a number of items, and we just want to know if it's positive or negative, then if a product or a quotient has an even number of negative factors, then the value is going to be positive. If the product or the quotient has an odd number of negative factors, then the value is negative. Okay, so what we're going to do, the strategy is going to be to move all the terms to one side so that it equals 0. Then we're going to factor everything, rewrite it as a multiplication of polynomials. Then we need to determine when that product is going to be positive or negative by identifying all the zeros, all the places where it equals to 0. In the places where the product equals 0, it will be a defining point on the number line where it changes from positive to a negative. So we can identify all those places, and then we can either use the test and check method, test the value in each one of those little sub-intervals, or analyze it in the way that I'm about to do. Okay, so the factoring technique that is described in these guidelines works only if non-zero. Okay, so for example, let's say we wanted to solve this, right? Already I can tell that this is not going to be a linear equation because there's a 2 there, and that's going to give me a quadratic of some kind. Okay, so let's move this way. So let's set up everything so that it is 0 on one side. So I'm going to copy this over here. I get x squared is less than or equal to 5x minus 6. So I'm going to subtract 5x from this side. I'm going to add 6. Subtract 5x from this side and also add 6, right? So maintain that inequality. So this inequality will still be in place. On the right-hand side, these guys canceled and these guys cancel, so I'll have 0. I know that adding or subtracting to both sides of inequality does not change the direction of the inequality, so I'm going to have it facing the same way. So x squared minus 5x plus 6 is less than or equal to 0. Good. So because I've set it equal to 0, what this is saying is, another way of describing what this is asking you is, find the values of x that produce a negative number here. That's what we want. Right? We want them to be less than 0. Find the values of x that result, that make this equation, that make x squared minus 5x plus 6 negative. Right? That's what this statement is asking. What values of x produce a negative number? Okay, so to do that, we're going to factor it. Now, that's this technique, and of course that depends on us being able to factor, so that's a whole nother problem, but okay, let's factor it. Here, it should be okay. We want two numbers that multiply to 6 and add to negative 5. So that should be x minus 3, x minus 2 is less than or equal to 0 after we factor it. That's true. That's true. Okay. And if we wanted to figure out when it equals exactly 0, x x minus 3, x minus 2 equals 0, right? That's one case, one thing we might be interested in. Now we can use the zero product property and separate this. This means that either this is 0 or this is 0, which means x equals to 3 is one solution and x equals to 2 is another solution. That's important to get, but it was really easy in this case, so we probably didn't need to do all that work. We can easily tell that if we let x equal to 3, then the whole thing will be 0. If we let x equal to 2, then the whole thing will be 0. And of course, because these two are equal to each other, that means that coming back up here, if I let x in here equal to 3, I replace that by a 3, replace that by a 3, I'm going to get a 0, right? 9 minus 15 plus 6 equals 0. That's true. And at the same time, if we replace it by a 2, 2 squared, minus 5 times 2 plus 6, that's going to be 4 minus 10 plus 6, that's also going to give you a 0. Okay, so we found the zeros of this, but that's not what they wanted. They wanted me to figure out when is this negative. Okay, so this is how I would recommend to do it. So I would do it. What we're going to do is we're going to come up with a number line that works for each one of the terms. Now there's 2 terms. If there was a more complicated case where you had 3 terms or 4 terms, then you're going to need more number lines. But here we only have 2, so let's do one for x minus 3. We're going to need another number line for x minus 2. And then finally, we're going to need another number line for the multiplication of the 2. X minus 3, x minus 2. Okay? All right, now we need to, these number lines are stacked right on top of each other. So the 0 is there, the 0 is there, the 0 is there. And then this is 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Maybe on the other side, negative 1, negative 1, negative 1. 1, 1, 2, 3, 4. Negative 1, 1, 2, 3, 4. Negative 1, 1, 2, 3, 4. Okay, so now for the first one, I want to find the 0. When I input a value of positive 3, this little multiplication becomes 0. Okay. And now, just focusing on this part, when I input a value bigger than 3, like a 4, a 5, or a 6, this little binomial here becomes positive. Right? You just simply test one value. 4 minus 3 is positive. So they're positive numbers in this direction. And by the same token, they're negative in this direction. If I let x equal to 2, 2 minus 3 is a negative. And that's going to be true over here. Okay, the place where we get a 0 is always the borderline between all the positives and all the negatives. Good. Okay, now we focus on this one. For this one, the 0 happens at 2. Here is my 0. And same thing in this direction. So as I put in values to the right of it, 3 minus 2 is positive, 4 minus 2 is positive. So they're always going to be positive in this direction. And therefore, they're always going to be negative in this direction. Good. Okay, so now we want to focus on the multiplication of the 2. So the multiplication of the 2, if I let x equal to 2, well, this first one is 0. So 0 times anything is going to be 0. So I know that this is going to give me a 0. And by the same token, this one, by the same property, this one's also going to give me a 0. Right? Because if we let x equal to 3, then that's going to be 0. 0 times 1 is 0, so it's still 0. Okay, now what we have is our number line is broken up into 3 segments. There's the segment that goes from negative infinity out to positive 2, the segment that's trapped between 2 and 3, and the segment that goes out from 3 out to positive infinity. So we just have to think about what happens when we pick a value of x that's to the right of 3. For both binomials, we end up with a positive times a positive, so everything on this side is going to be positive. Okay. On the other side over here, we end up with a negative times a negative, right? If we pick any value of x over here, both binomials give you negatives, and negative times a negative equals a positive. So I know that all those values are going to be positive over there. And then in the middle, between the 2 and the 3, if we pick a value of x somewhere in the middle, this binomial results in a negative, this binomial results in a positive, and negative times a positive will be equal to a negative. Okay. So what we've concluded is that if x equals something over here, the product of the two is going to be positive. If x is a value between 2 and 3, then the product of the two is going to be a negative. And if x is a value to the right of 3, bigger than 3, then the product of the two binomials is going to be positive. So based on all this, we can come back and answer the question we wanted to figure out: what values of x produce a negative number? And here it is, it's these. Now, it was less than or equal to 0, so that means we include the endpoints. Good. So our solution is let x, well, there's different ways of describing it, so let's do it in different ways. One solution set could be written this way: 2, 3, with brackets to show that we want to include the endpoints. Another way to describe it would be with a graph. With a graph, we would just draw a number line and put a 2 there, put a 3 there, and then either put a color if you can, or if you're just working with pencil, you don't have colors. I'd like to do a little squiggly thing. So a little squiggly thing like this between 2 and 3 really clarifies that it's that part of the line segment that gives us the solutions we want. And maybe you might want to include the 0 so people just kind of give them context of where we are on the number line. Or we can also use inequalities and say that x must be the values trapped between the values 2 and 3. Every value between 2 and 3. Good? Questions? We can also use set builder notation, which is similar to this. We can just say that it's going to be, and now you don't have to use, well, okay, x. The solutions are going to be x such that x is every value trapped between 2 and 3. Any questions? No? No? So I like to do the 3 number lines to organize these. You know, when they get more complicated, it's just easier to add more number lines. And you know, just the way I like doing it. But there are other ways to do it. You can organize the information in different ways. Another popular way to do this is simply to identify the zeros. So you do this same thing and you move everything to one side, set it equal to 0, factor it, find the new zeros. These zeros break up your number line into different segments. And then what people do is just test points. Pick something in this section, plug it in, either to your the binomials, the factored form of your polynomial, or back to the original polynomial, either way. So pick a test point and check to see whether that value is positive or negative, and then kind of reconstruct the whole thing that way. So that's the way that the author chose to do it, I think. So here's what the author did. So they factored everything, right? So moved everything to one side. But we have a 0 on one side, factored it. That creates the points on the number line, so it breaks it up into 3 segments. Everything to the left of 2, everything to the right of 3, and then the one in the middle. So then you can just pick any convenient point. What's a convenient point to the left of 2? Well, it seems to me like this is a nice convenient point. What's a convenient point definitely between 2 and 3? Well, how about 2.5? That's a nice convenient point right in the middle. And a convenient point over here, well, you could go with 4, could be a nice convenient point. or maybe 10, just because powers of 10 are sometimes easy to work with. So pick a convenient point, test it out, and see if you get positives or negatives when you do that. Good. So they pick some test values. So they use the test value of 1 to the left of 2. They used 2.5, and then they used 4. So you just plug it into your equation and determine whether it's positive or negative for each of those sections. So that's how they create the little table here to determine when it's positive, when it's negative, and figure out the sign of each of those regions. So putting it together like this. And finally, you get to the same answer we got. Okay, so it's just a matter of organizing it in a way that makes sense to you. I will accept any way you want to do it. Whatever makes sense to you is fine with me. Are there any questions? No, no, no. Okay, moving on to absolute value inequalities. So these get a little trickier. So these are the core ideas we want to cling to when we want to solve an absolute value inequality. Okay, so remember the definition of an absolute value. An absolute value of x means that we're looking at all the values. I'll just try this. All the values of x that are x units away from 0 is one way to look at it. So this is the definition of an absolute value is less than some constant c. So if we had, let's get rid of this color. So for example, if we had that the absolute value of x was equal to 3. Let's look at the equality for a second. Absolute value of x equals 3. What kinds of values can I put in here? Well, obviously x could be a 3 or it could be a negative 3. Right? Just kind of thinking about what an absolute value is. We can either plug in a 3 or we can plug in a negative 3, and both of those would give us a true statement. On the number line, that means that if we have here 0, we can go over here to positive 3, or we can go over here to negative 3, and both of those values give you a true statement. So one way to think about this is the distance that that value is away from 0. Right? If we were kind of measuring this distance here, it would be a distance of 3. If we were measuring this distance here, it would be a distance of 3. Good. So remember, measuring the distance has no sign. So whether we go to the left of 0 or to the right of 0, it should be a distance of 3. Right? So the distance away from 0, when the distance away from 0 equals to 3, then x must either be a positive or a negative 3. So if we just change it to an inequality now, if we were looking at absolute value of x is less than 3, what values can we plug in here? Well, we can plug in any one of these things and it would be true, right? The absolute value of 2, okay, that's going to be 2. 2 is less than 3. The absolute value of 1, that's going to be 1. 1 is less than 3. So any one of these values in here makes this statement true, but also any one of these values in here, all these little negatives here, also make this true. So that's how we get this graph here. Any value trapped between negative c and positive c, any one of these values makes this inequality true. Right? So by definition, the absolute value of x is less than a constant means that x is all the values trapped between negative c and positive c. Similarly, if we had less than or equal to, then all we have to do is introduce the fact that we're allowing it to be that endpoint. So absolute value of x is less than or equal to c means that x is all the values that are greater than or equal to negative c but less than or equal to c. This one gets a little trickier. Absolute value of x is greater than c. So again, going back to this, if I had the absolute value of x is greater than 3, what kinds of values can I replace the x by to get a true statement? So the right-hand side of this answer is usually easy to think about. What kinds of things can I put in there to make this a true statement? Well, one of those things is really big numbers. How about 8? How about 10? How about 107? Like all of those numbers can go in here, and the absolute value of those numbers is definitely greater than 3. So I can get this side of it pretty easily. Really big numbers, numbers that are bigger than that constant. It's the other side that usually confuses people, because the other side of this is that the other thing I can plug in here is numbers that are far left on the number line. So for example, -5. The absolute value of -5 is +5, and +5 is bigger than 3. So I can also plug in numbers that are really, really to the far left of the negative C value, right? So in this little example here then, if I wanted to create a number line that represented the solution, absolute value of x is greater than 3, then here is 0, here is 3, and I know that plugging in very large numbers, so I can put a parenthesis, plugging in very large numbers is going to be one side of the solutions, but then the other side, the side that most people get confused on, comes over here, and notice that I'm saying that it's greater than 3, so I have to make this -3. Good. So this is a +3, but I make that -3. And then values that are to the left of that, from -infinity up through -3, these are the other side of this equation. Putting in a -5, a -10, a -20. Those very large negative numbers, when I find the absolute value, make very large positive numbers that are bigger than 3. Good. And then we can do the same thing as before by considering the greater than or equal to, and that just means that we include the the actual value. Good. So when absolute value of x is less than a positive constant, we can combine it into this type of three-way inequality. But when the absolute value of x is greater than a constant, then really we have to do two separate inequalities. X has to be less than its negative, or x has to be less than, x has to be greater than that constant. Any questions about these? All right, let's try an example. For example, solve for x. Find all the values of x that make this a true statement. So because we're looking for all the values that are less than 2, right, within 2, then we can just use our property to say that this must mean that x minus 5, this is less than 2. I'm looking for all the values where the thing inside here is less than 2. But at the same time, I'm looking for all the values where this thing inside is greater than -2. Good. And here I'm just using property number 1. Absolute value of something is less than a positive constant c. So I just get this. And once I get to a three-part inequality, then all I have to do is solve it, keeping in mind the rules of inequalities. I can always add or subtract the constant, and that does not change the direction of the inequality. So these combine to give me 3 is less than x is less than 7. And so that's my answer. Right? So it's either this, or I can put it on a number line and say that it is all the values between 3 and 7. All these values in here with parentheses to show that we do not include the endpoints. So here's one solution or another solution. Any questions? No.
Oh yeah. Question, but like it's not towards the topic.
Okay, yeah.
You know how like you're writing on the PowerPoint right now? Is there any way you can like save these and put it in Canvas?
Yes, sure. You mean with my writing?
Yeah.
I think so. I can do it. I think that on the other side, though, technology, there might be some versions of PowerPoint that don't open this with the writing. So if you have an older version, or I'm not really sure what the technology issue might be, but it from experience it seems like there might be some sort of problem in terms of the specific version of PowerPoint that you use. So some of you out there might not be able to open it if I solve it, or if I save it with this. So I can put both the original as well as this, but just to hopefully prevent any confusion, if you try and open one of them, it might have a different kind of file extension on there that your system might not be able to open. And then it further complicates things because I'm using a Mac, and of course PowerPoint is a Windows product, and so this is a cross product, and it wasn't originally meant to work with each other, and sometimes they have hiccups. But at any rate, I'll try and put them up as I do them, and you should have access to them, hopefully.
Thank you, because that would help a lot, honestly.
Okay. And then, of course, these all get recorded and put on YouTube, so you can always, the value of that is you can always fast forward, pause, rewind, do whatever you need in order to get these. Right? Especially since, I might be going kind of fast if you're trying to copy these down. If you missed a little something, then just going on to the video and just catching the part that you missed, might be a nice way to do that.
Yeah, totally.
Cool. You. No problem. Okay. So let's see. The author solved it in the exact same way, so then they got that. Modeling with inequalities. Modeling real-life problems frequently leads to inequalities because we are often interested in determining when one equality is more or less than the other. Okay, so let's look at this. A carnival plans for tickets. A carnival has 2 plans for tickets. Plan A, you can pay a $5 entrance fee and then pay a quarter for each ride. Plan B, you can pay a $2 entrance fee and 50 cents for each ride. How many rides would you have to take for Plan A to be less expensive than Plan B? Okay, so clearly if we are doing very little, like let's say we only go on 2 rides, under this plan, I would have to pay 50 cents from here, right, because it's 25 cents per ride, plus my original $5 entrance fee, so I would have spent a total of $5.50. So clearly this question was written like in 1950 or something, because who goes to a carnival and spends $5.50? Anybody know what the Disneyland prices were before they closed? In the neighborhood of like $150, like $200 a ticket. And then they further break it down by whether you want to go to one park or both parks. Do you want to have the freedom to go back and forth between parks? Right, those are all different prices. So yeah. Any rate, okay, so the second plan, if I'm only going to do 2 rides, if I'm thinking, man, I'm just going to go in there, I'm going to ride 2 things, and I'm going to go home. Okay, under this plan, well then, for the rides, I would pay $1 from here, 50 cents each, so $1. Plus my original $2 fee to get in, so in this case, I would only end up paying $3. So in the event that I'm only going to be doing 2 rides, clearly Plan B is better. But if I'm going to be doing a lot of rides, eventually this 50 cent per ride thing is going to get pretty expensive. So we want to set up some sort of inequality to figure out when they equal each other, and then when one plan is definitely smaller than the other plan. So this one should be fairly easy. So total cost of X number of rides should be, well, under Plan A, My total cost, plan A. Well, I went to, there was a $5 entrance fee plus 0.25 times x. That was my total cost in the plan A. And then under plan B, there was a $2 fee plus 0.5 times x number of rides. So this is my total cost under plan B. And then the question was, how many rides would you have to take for plan A to be less expensive than plan B? So maybe that's what we're looking for. Find the values of x so that this plan is still less expensive than that one. Okay, so that's what we got to solve. That should be fairly easy. Okay, so x is the number of rides. Under plan A, it's 5 plus 0.25x. Under plan B, it is 2 plus 0.5x. So that's the inequality we need to solve. So 5 plus 0.25x less than or equal to 2 plus 0.50x. Okay, so let's simplify these. Luckily, they're linear equations. So let's subtract 2, subtract 2. Adding or subtracting does not change the direction of the inequality, so that'll be 3 plus 0.25x is less than or equal to 0.50x. And then let's move this over here. Minus 0.25x minus 0.25x, which gives me 3 is less than or equal to 0.25x. And then dividing both sides, we get 3 divided by 0.25 less than or equal to x. Dividing by both sides by of inequality by a positive number that again does not change the direction of the inequality. And this goes into it 12 times. Right? A quarter goes into $1 4 times, and there's 3, so that should be 12. It's less than or equal to, less than or equal to x. So x must be bigger than 12. If you ride more than 12 rides, then the plan A becomes cheaper. So going back to here, we have 5 plus 0.25x less than or equal to 2 plus 0.50x. So at 12, you're going to find that both sides are equal to each other. But when you get larger than 12, 13 rides, 14 rides, 15 rides, you'll start to see that plan A is cheaper. This inequality is true when this is true. So plan A is less. Plan A costs less when x is greater than or equal to 12. More than 12 rides. 12 or more rides. If you're going to do less than 12 rides, then this is still cheaper. Questions? Questions? No? You're good? Okay, so I think this is a fairly easy section. 8, what do we got for 1.9? Okay, yeah, super easy. This is just dealing with the coordinate plane, some basic properties of coordinate planes, and maybe a couple of extra little things. So 1.9, the coordinate plane, graphs of equations and circles. So the coordinate plane, the distance and the midpoint formulas, graphs of equations in 2 variables, intercepts, circles, symmetry. Okay. So the coordinate plane. The coordinate plane, also known as the Cartesian plane, it's the intersection, perpendicular intersection of two real number lines, right? So we have a horizontal number line, which we often call the x-axis, and then we have a vertical number line, which crosses at 0 with the x-axis. That is typically called the y-axis. Right? So this is what it looks like. Sure, we've all seen it many times. So here's one number line in the horizontal direction. And then at 0, we have this vertical number line. You can kind of tilt your head and see another number line. So the number line on the horizontal axis is the traditional positives in this direction, negatives in this direction, 0 right there. And the vertical number line has positives in this direction, negatives in this direction. That divides up our space, our two-dimensional space, into 4 quadrants. Quadrant 1, 2, 3, 4. We call that counterclockwise. If you remember those old-school traditional kind of clocks with a little hand, it ticks in this direction. We're going to have to come up with a different way of describing this because more and more people don't know what that is. At any rate, counterclockwise goes in this direction. Is there anything else that we can use to describe counterclockwise instead of a clock hand?
Have you heard of the cast method?
Cast method? No, what's the cast method?
Like the C-A-S-T, so C would be in quadrant, or in the first quadrant, A would be in the second quadrant. I think this is more for trigonometry because I learned this in my trigonometry class.
Okay.
I was just wondering.
What do you do with, like, what's the, let me write it down.
Well, to be completely honest, I don't really know, so I was hoping you could shed some light on that.
I see. Okay, so C-A-S-T? Like that?
Yeah, that's correct.
Have other people heard of this cast method? My suspicion is that this has something to do with tricks, some sort of trick to help you remember things like cosines and sines and tangents and that kind of thing. And we'll get to trigonometry. Again, a lot of this is review, so for hopefully for all of you guys, the chapters 5 and 6 and 7, which are the trig sections, will be familiar, but I do present it in a slightly different way, I think, than most people. Not that it's wrong the way you learned it, it's just different. My philosophy is just a little bit different, particularly with trigonometry, right? So I don't believe in memorizing any tricks to know the answer. So there are a few fundamental things you have to memorize, but I can count them on one hand, the things you have to memorize, and everything else should be derived from those. You know, there's a lot of these kinds of trick things that people know that I've never even bothered to look at, and I don't remember. So like Sakatoa, CAS, all those other things are just memory tricks to get to the answer. But I don't like them because very often people memorize the trick and then don't really ever really connect to the actual answer or what it means. You just know how to get to the answer because they remembered some sort of trick. You know, after the O, you always divide by the A, and that's your answer. Like, okay, what does that mean? I don't know, but whatever, that's the answer. At any rate, so we'll get to it when we get to trigonometry. But for now, back to basics here. We're just looking at coordinate systems. And so we get the quadrants 1, 2, 3, and 4. Also, very important, this isn't the only way of creating a coordinate system. It's just the most popular and the one we use the most. But we will in this class use a polar coordinate system, which has some advantages, some disadvantages as well, but it's just different. So it's nice to compare it to something, a different idea. Anyway, in a coordinate system, then each point in our two-dimensional grid is identified by an ordered pair, which we use the notation of A comma B with parentheses, right, where A represents the distance along the x-coordinate or the horizontal axis, and b is a value along the vertical axis or the vertical coordinate of our point, right? So any point on our grid, for example, 1, 3, means that we go 1 unit this way, 3 units up, and then we arrive at our destination. Right? So it's important to remember that the first value is always along the x-axis, the second value is always along the y-axis. So hopefully that's all pretty clear. If we have this, remember this is set builder notation. Set builder notation can be used to describe a region of our two-dimensional Cartesian grid. So for example, if we have ordered pairs, so here remember this describes what one typical value in our set looks like. And then we have this bar, which we should read as such that. So x comma y such that. And then over here we have conditions. And so the only condition we have here is that the x must be greater than or equal to 0. So we're looking at all the places where x is positive. So if we think of our number line, our Cartesian coordinate system, something like this, and I'm trying to identify all the points that satisfy this condition, and the only condition that we have is the x better be positive, then a point, say, over there would satisfy it because the x is positive and the y is positive. A point over here should satisfy it because the x is positive and the y is negative, but there was no conditions on the y. The y could be anything. So as I keep thinking about all the points that satisfy this, eventually we arrive at the idea that it's all of these points over here. Anything on the right-hand side, everything in quadrant 1 and quadrant 2. And because it was greater than or equal to 0, it also includes the actual y-axis. So everything to the right of the y-axis is described by this set. Good? Questions, questions, questions? So there's the y-axis, here's the x-axis. What about this one? Now we have a separate condition. The condition is x comma y such that y better be equal to 1. Y better be equal to 1. So let's again think about all the possible answers. As I think about a point, right, an ordered pair x comma y such that y is a 1. The y is in this direction, so y being 1 is like there. So for example, that point of 0 comma 1 would satisfy this. The x doesn't have any restrictions, so also negative would be okay. Negative 1 comma 1 would also be okay. Or say 3 comma 1, right? So anything as long as the output, the second value, the y is a 1. So if we think about it, then this begins to form a straight line. A straight line is described by that, right? Which we also describe as the line, the line y equals to 1. Good. Finally, this last one, again, it's a bunch of ordered pairs, and the only restriction is that the absolute value of y is strictly less than 1. So very, very small positive values of y, values that are less than 1, are going to work. And then also small negative numbers, when we take their absolute value, they will also work. They satisfy that, right? So the only thing that fails, for example, is like if I let y equal to 2, absolute value of 2 is 2. 2 is not less than 1, that fails. Or even if it's a negative 2, absolute value is still positive 2, that is not less than 1, so that fails as well. So this restriction is really just saying that y, as we saw earlier, y has to be all the values trapped between negative 1 and 1. There is no restriction on the x, so the x can go anywhere, but the y has to be fairly close to the x-axis, fairly close to y equals to 0. So if we think about that for a while, we see that it's going to create a little tunnel like this. All the values trapped in between these two, all the ordered pairs trapped in between these two, will be described by that guy, where this is the line y equals to 1, and this is the line y equals to negative 1. Any questions? Okay, so there's that first one, the right-hand side of the number line, just the line y equals to 1, and then that little channel there. And also note that there are little dotted lines here to show that we don't actually let y equal to 1 or -1 because it was a strict inequality. Good. The distance formula. Well, the distance and the point formula. Okay, so the distance between two values on the number line was just equal to b minus a, and really it could also be a minus b. It doesn't matter. We just have to subtract them. But we know that distance has to be positive, so we can take the absolute values. If you knew for sure which one was the bigger one, which one was the smaller one, then you wouldn't worry about the absolute values. But since we don't necessarily know that, we do have to include them. So what this means is if we have, say, on the number line, here is 8 and here is 5, and we want to know the distance between them, of course we would just take 8 minus 5 and go, yep, it's 3. So the distance between these two numbers is 3. But when we have just some value a and b, we don't necessarily know whether it's true that a is over there and b is over here, or maybe the other way around. Maybe a is over here and b is over there. Traditionally, we like to write them this way. Traditionally, we like to think that they go in this order, but there's no guarantee that that's true. If I know that this is the way it is, if I know that a is the bigger number, then the distance is going to be a minus b, right? Because it's the bigger one. And if I knew that it was in this direction like this, well, then I would know it's a b minus a. And I would know that both of these give me a positive answer because I know that this one's bigger. But since we don't really know which one is bigger and which one is smaller, then what we have to do is slap an absolute value around them, and then I'm guaranteed that the answer will be positive. And it won't matter anymore. So it doesn't really matter whether you think of this formula as absolute value of b minus a. It's the same thing as saying it's the absolute value of a minus b. So the order doesn't matter as long as you have absolute values. Is that okay? Any questions about that? No? Okay, so that's on a number line, but we want to get a little more creative because we want to think about the distance between 2 points on a rectangular coordinate system. So let's say that we have some point over here and some point over here. And now just to put some numbers on them this time before we jump into all the variables, let's say that this point here is at distance 1 and this is distance 2. So this is the ordered pair 1, 2. And then over here, let's say that this is way out here at distance 5. And let's say that this thing up here is at distance 7. So this is the ordered pair 5, 7. And we want to find the distance between these 2 points, right? It's going to be this value right there. Right? I can get my measuring tape. I want to figure out the distance between these 2 points on my Cartesian coordinate system. This is x and this is y. Okay, so the trick is going to be to realize that what we could do is think about this triangle here. We can extend this line there, we can drop this line there, and what we have is a nice right triangle. And what I could do is I can find this distance, which is going to be 5 minus 1, or just 4. And I can find this distance, which is equal to 7 minus 2, which is equal to 5. And then I can use my Pythagorean triangle. Okay. I know that a, b, c, we know that a squared plus b squared equals to c squared. So applying that to here, well, okay, this is the distance we want to find. And remember that we use this notation. Distance between, okay, let's call this point A and point B. So A is this point and B is this point. So distance between A and B, that distance right there, that's going to be the hypotenuse. So we get the formula that the distance between point A and point B squared must be equal to, well, just using these specific numbers, it must be equal to the 4 squared plus the 5 squared. And so then we can take the square root of the whole thing. Distance A and B must be equal to the square root of 4 squared plus 5 squared. And when we take the square root of both sides, traditionally we have to consider both options. So we'd have a plus and a minus thing here. However, I know that the distance is specifically a positive value, so we just ignore the negative. Ignore the negative. Good. So this would be 16 plus 25. So that's what, 36? No, wait, 41. So square root of 41 is the distance between point A and point B. Any questions about this? No? Good. Okay, so now we want to recreate the same thing in general. So just using a bunch of letters. So we got point A, we got point B. Point A is some x sub 1, y sub 1, right? Instead of having the specific numbers of 1 and 2, instead of just having 1 and 2, we just have x sub 1, y sub 1. And we have some other point over here, x sub 2, y sub 2, point B. And again, we find this distance. We found that distance by subtracting these two things. Now, why is that? This is a little mistake here. This should be x sub 2, and this should be corresponding to y sub 2. Okay, so we find this distance here by taking this number and subtracting that number. But again, if we don't really know which one's bigger and which one's smaller in general, then we can slap in these absolute values and guarantee that we get the positive distance between two numbers. Same thing in this direction. We get y sub 2, y sub 1, and then we put the absolute values. Now, you might be asking, well, I can tell x sub 2 is bigger. Why do I need the absolute values? Well, if this was the real picture, sure. But the original question doesn't necessarily tell you that x sub 2 is the larger number. So we're just kind of drawing a picture to kind of visualize this. But nobody really told me that x sub 2 belongs there. It could be that x sub 2 is there and x sub 1 is there. So we don't really know which one's smaller and which one's bigger. When we don't know, then we put the absolute values to guarantee that we get the distance between them. It eliminates the possibility that we accidentally get a negative number. Okay? And then we just use the same property again to say that this side squared plus this side squared is going to be equal to this side squared. Pythagorean theorem comes through again. Good? And so we get our distance formula. Taking the absolute value of x minus 1 in absolute values, that guarantees that it's a positive number. The output is positive. And then when you square it, well, you also get a positive number. So this right here can be simplified by saying, well, it's just this, right? Because it doesn't matter whether this part in here is positive or negative. When you take it square, you're going to get a positive output. You get the same answer. So it doesn't really matter that we take the extra step of making sure to make it positive with the absolute values and then squaring it. Kind of save yourself a step. You don't have to do the absolute value and then square. You can just square it. So it just simplifies the formula just a little bit. Good. Questions, questions, questions? For example, which of the points, point 1, comma, negative 2, or point Q, 8, comma, 9, is closer to the point 5, comma, 3? Okay, so we just got to find the distance between point A and point P, and the distance between point A and point Q. So A and P, okay? So looking at our formula, it's really a pretty easy formula to work with. It's going to be the difference in the x's squared plus the difference in the y's squared. And it doesn't matter which is which when you do this, because again, you're going to square it, so it doesn't really matter. And then you take the square root of the whole thing. So it's a very easy formula. So if I want to find, for the first one, the distance between the A and the P, these, I'm going to subtract the x's. The 1 and 5 get subtracted. And it doesn't matter whether you write 5 minus 1 or 1 minus 5. Either way, after you square it, you're going to get the same answer of 4 squared, or 16. And then the difference in the y's. So the 9 and the 3, the negative 2 and the 3 get subtracted. And again, it doesn't matter whether you do that or you do that. Either way, after you square it, you're going to get a 25. Either way, you get square root of 41. Good. And then for the distance between Q and A, you subtract the x's, square them, subtract the y's, square them, and you end up with square root of 45. So let's just kind of get a sense of where these points are. The y-axis, the x-axis, just to kind of get a rough idea of where these are. That's 1, 2, 1, 2, 4, 4, oops, 5, 9, 2, 7. 2, 7. 5, 9, and 2, 7. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. Okay. 1, 2 is going to be somewhere over here. Let's put it up. Something like there. 1, 2. 1, 2, 3, 4, 4 somewhere over here. 5, 9. 5, 9 is like up here. And 2, 7 is going to be somewhere like around here. Okay, so we have something that looks roughly like this. And we're trying to establish if it's a parallelogram. In order for it to be a parallelogram, it must be true that this, when we look at that and compare it to this one, you want to show that they bisect each other so that this is exactly the same distance as that one, and that this one is the exact same distance as this one. So, of point of interest is right there. What is that guy right there? So we can figure this out. Where does it land? Where does it go in the middle? Okay, so we have this point here. Let's put all the points back in here. This one was 1, 2, And up here, this is 4 comma 4, and then 5 comma 9. Let's see with that. Okay, 5 comma 9, and then 2 comma 7. So I want to use the midpoint formula between these two to figure out that point, and then find the midpoint formula between these two to figure out that point. Hopefully they give me the same point. So the midpoint formula is easy. Midpoint between 2 points is just going to be to add the x coordinates and divide by 2, add the y coordinates and divide by 2. So what's the points? PQRS. PQRS. So this was point PQ, R, and S. So between P and Q, P and R, we want to add the 1 plus the 5 and divide by 2. Midpoint. And then we want to add the, oh man, add the 9 and the 2, 9 plus 2 and divide by 2 to give us 6 over 2 and 11 over 2, or 3 and 5 and a half. Good. In the other direction, the midpoint between S and Q, then we add the x's together. 4 plus 2 divided by 2, and the 7 plus the 4 divided by 2 to give us the same thing. 6 and 11 over 2, or 6 over 2, sorry. So 2, and so 3 and 5.5. So the midpoint formula tells us that it's the exact same point. Here's a nicer way of doing that. So each diagonal bisects each other. Questions? 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 No? No? Graphs of equations in 2 variables. So an equation in 2 variables, such as y equals to x squared plus 1, expresses a relationship between 2 quantities. A point x comma y satisfies the equation if it makes the equation true when the value for x and y are substituted into the equation. So for example, here's some equations. We have y equals to x squared plus 1. One possible solution would be to replace the x with a 3 and the y with a 10. And so we get that 10 is equal to 3 squared plus 1, which is true, right? This is going to be 9 plus 1 is 10, so 10 equals to 10. But on the other hand, if we replace the x with a 1 and the y with a 3, then 3 does not equal to 1 squared plus 1. So there are some ordered pair solutions that work and some ordered pair solutions that work. Your mission would be to find all the values that do work, all the values that don't work. Okay, so the graph of an equation in xy is the set of all points xy in the coordinate plane that satisfy the equation. Okay, we know that. Okay. Sketch the graph of the equation 2x minus y equals to 3. Okay, so how do we work with that? Okay, so we need to solve for y. That's easy, right? So what we have to do is move all the terms from one side. On the other side, we can isolate the y. So that's plus y. So that would get us to 2x 2x equals to 3 plus y, and then minus 3, minus 3, minus 3. That gets us to y equals to 2x minus 3, which is this equation right in here. Okay, and then we can just kind of guess and check. So right now we're just kind of guessing and checking different values. So if we let x equal to negative 1, we can plug in a negative 1 into this equation. Right, so we're going to let negative 1 be plugged into there. So we end up with negative 2 minus 3 gives you negative 5. So there's the ordered pair of the solution. If we, on the other hand, let x equal to 0, 2 times 0 is 0, minus 3 gives you negative 3. There's another ordered pair that works, and so on and so forth. So when you have it in this form and you've solved for y, we can just plug in different values of x and be able to get the resulting value of y. That gives us ordered pairs. Okay, so we've worked with these before. And then we can take all those ordered pairs and create a graph for all of them. So here is a nice graphical description of all the ordered pairs that solve our linear equation. We found the constants, the simple values of x with this nice table, negative 1, 0, 1, 2, 3. But of course, there's an infinite number of decimals that will also work. Luckily, with a graph, we get to see the pattern. And so we don't have to evaluate every single little decimal. We can just kind of represent all of the answers with this solid line there. Right, so any value on the line is an ordered pair. Right? You shouldn't really think of this as a solid line. In some respects, it's nice to think of it as a solid line. But in other respects, it's nice to think of this as an infinite number of ordered pairs such that the ordered pair solves this relationship. Intercepts, the x-intercept, the y-intercept. So the x-intercept is the place where this graph will cross the x-axis. Right? So looking at this, if this is our graph, then this point, this is our graph, then this point right here is the x-intercept point. X-intercept point. And this point right here is the y-intercept point. If I come up with the ordered pair value to this one, well, remember the ordered pair always has the x-coordinate first and then the y-coordinate. And because it's on the x-axis, it must be true that the y-coordinate is 0. So it's x comma 0. And then on the other hand over here, if I come up with an ordered pair to this point, the x-coordinate is 0 and the y-coordinate, well, I don't know what that is, so it's just some y. So x comma 0 describes our x-coordinate, right? And that's because the y value, y-axis, the y-coordinate equals to 0. Whereas over here, 0 comma y is the y-intercept, which means that the x-coordinate equals to 0. So when we have an equation like this and we want to solve it, in order to find this x value, what we do is we let y equal to 0. Right? To solve for the x-intercept, we let y equal to 0, and then solve it, and then that'll give me the value of x. On the other hand, if I wanted to find the y-intercept, we would let x equal to 0 and solve it. Well, this one's easy since that becomes y equals to negative 3. So I can easily tell in this equation that this y-intercept is the point 0 comma negative 3. Good. And if I set the other one up, 0 equals to 2x minus 3, and moving a 3 over, we get 2x, and dividing it, we get a 3 over 2 equals to x. So I can see that the x-intercept is going to be equal to, it's going to be equal to 3 over 2 comma 0 for the x-intercept. But in general, that's the form that the pattern we're going to take to solve these things. We're going to set them equal, to find the x-intercept, we're going to let the y equal to 0 and solve. To find the x-intercept, we're going to let the x equal to 0 and solve. Right? So an equation, sort of a graph of any kind could have several of each. So here's some examples where the curve has 3 different x-intercept points for the first example. Okay. So for the first example, we have 1, 2, 3 different x-intercept points. This thing is not cooperating. Okay. Thank you. So we have 1 there, and 1 there. And for the second example, they're showing you how it might have more than one y-axis intercept point. Okay, but either way to solve them, we set the y equal to 0 and solve for x to solve for the x-intercepts. To find the y-intercepts, we set x equal to 0 and solve for y. Good. For example, find the x and y-intercepts of this equation. So y equals to x squared minus 2. So to find all the x-intercepts, we set y equal to 0. And so 0 equals to x squared minus 2. And so we solve it by adding a 2 to both sides. So we're going to plug in y equals to 0 here, and that's how we get this. And then we're going to add 2 to both sides. We're going to decide, then we take the square root, we get plus or minus square root of 2. So here are our 2 intercept points. And as ordered pairs, they combine to the square root of 2 comma 0 and negative square root of 2 comma 0. On the other hand, if I wanted to find the y-intercepts, then all I have to do is let x equal to 0, which makes it really easy and solves it as y equals to negative 2. So this just translates into the ordered pair 0 comma negative 2. When you're translating into ordered pairs, be careful, because remember that in the ordered pair case, it's always x comma y, regardless of which one is the first value you knew. So we started out with x equals to 0, whereas over here, people often confuse these in the other way around. Right? No matter how you solve these, when you find your ordered pair, it's always in the form of x, then y. Good. Okay, so if we graph that equation, x squared minus 2, well, we know that it is related to, similar, or associated with this equation, which is one of our standard equations. Y equals x squared is a standard parabola centered with a vertex of 0, 0 on the origin of the graph, and subtracting 2 shifts the whole thing down by 2 units. So hopefully that's one way to kind of sketch this thing. Okay, and so we have our 2 intercept points, x-intercept points, and y-intercept point. So the y-intercept we said was equal to 0 comma negative 2. And the 2 x-intercepts are positive root 2 comma 0 and negative root 2 comma 0. Questions? Good. Okay, I think this is a good place to pause. Oh, yeah, question?
Yeah, I mean, this is just a personal question.
Yeah.
I mean, I can ask after, you end the meeting, if that's okay.
Oh, okay. Are there any questions? Oh, is it math related or something about your own?
Yeah.
Oh.
It's about yesterday.
Oh, okay. Well, are there any more questions from anyone else about this stuff right now? Intercepts or anything for now? No. Okay, so this is a good place to wrap up this section, and we'll come back tomorrow and we'll pick up with circles.